Hello students, this is Amada R, Assistant Professor from the Department of Robotics and Automation. Our subject code is MR3491. Our subject name is Sensors and Instrumentation. Today we are going to discuss about Unit 3, Part 3, right? So topic is current sensors. So today in this session we will discuss about the current sensor. So current sensor which detect and measure the AC and DC electric current which flowing through a conductor. It detects both AC and DC electric current, okay, which is flowing through a conductor, and it converting into a proportional or usable signal for monitoring and also a control or a safety, okay. So here the essential for power management and motor control, they are energy enable efficiency, prevent overcurrent damage, and were vital for applications like electric vehicles and renewable energy system. That's why we are using the current sensor. These current sensor concepts include Ohm's law, Faraday's law of induction, and magnetic field and optical sensing. So first we'll see about the Ohm's law. Okay, sensor concepts. This is the current sensor concept of Ohm's law, that is shunt resistor. Shunt resistor also a current sensor. So these are the precision resistor with a low resistance that are connected in series with the current carrying wire, that is in your diagram, that is current carrying wire. The voltage drop across the shunt resistor is proportional to the current flowing through it. That is the voltage drop across this is the shunt resistor, okay, this is the shunt resistor. The voltage across this is proportional to the current flowing through it, and this voltage may be measured to find out how much current passing through it. Why we are measuring this voltage? How much current passing through this conductor, okay. So that's why we are using the voltage. So shunt resistors are capable of measuring both AC and DC currents because the shunt resistor is in the current conducting path. Because the shunt resistor is in the current conducting path. That's why this measuring both AC and DC currents. Okay. So it can cause considerable power loss that grows with the square of current. In high current application, the power loss may limit the usage of shunt resistor. So we can't use the shunt resistor in a high current application. Okay. So in this diagram, there is a shunt resistor for a current sensing. So this is the shunt resistor with a current and also a voltage which gives to the amplifier, and the amplifier amplified voltage is gives to ADC, and that transfer to the controller. Only after amplification it will give to ADC and also a controller. We will remember this. Next one is current transformer. Current transformer is also a current sensor. So it has a main winding, a core, secondary winding. I will show you. It's a effective AC current measuring sensor. Okay, here is the basic construction of a capacitor current transformer. So this is the hollow core, this is the primary current IP, and this is the main primary conductor, and these two lines are the winding. This is the copper winding, this winding is a secondary winding, this winding is a secondary winding. So here primary current IP, which we will give the AC voltage AC current to the this primary current, then it generates the magnetic field to the secondary winding. Okay, so this is the operation. We'll get the current from the ammeter. So here the voltage is proportional to the current. Okay, so this figure to illustrate depending on the turns ratio, the change in the main current IP is reflected on the secondary side. Okay, here the IP is the primary current. This is reflected to the secondary winding, so which may be utilized for sensing. A shunt resistor that generates the output voltage proportionate to the primary current. Yeah, in the shunt resistor, the output voltage is proportional to the current that can be monitored in the output current. So this provides, but this uh, current transformer provides the isolation, minimal losses, straightforward operating principle, and also a voltage output. Here there is an important point. It does not require the extra amplification current sensor. But in shunt resistor we want the amplification factor. But in this we do not want the extra amplification for current sensing. Okay. So this need a ADC converter for output to sample a voltage directly. Okay. To sample a output voltage directly. Next one is a magnetic field sensor for current sensing. It's very difficult to detect a current and generate a static magnetic field using a Faraday's law induction. So in other hand, magnetic field sensor can identify both static and moving magnetic fields. So they present themselves as a desirable alternate choice for current sensing. Hall effect sensor. Hall effect sensor are usually in variety of applications. So already I told you Hall effect sensor it measures the current and how we can see in the diagram. This is the Hall effect principle. This is the Hall element. In the last session we will discussed. Here is the current. We will give the excitation AC, the excitation here only, and from this and this knob the magnetic field will be generated. When current we will give the AC current to this, and it generates the magnetic field, and we can measure the Hall voltage in term of EMF. We can measure here is the output voltage. Okay. The principle is a Fleming left hand rule. Okay, already we discussed. Here is the use of Hall effect current sensing. This is the conductor, that is the primary winding, and so this is the magnetic core. This is the magnetic core. In the magnetic core, our Hall element is used for current sensing. It uses the amplifier, and it amplifies the current or output voltage, and it gives the output. So this is the conductor. Okay, this is the Hall element which is used for current sensing. Next one is a flux gauge sensor. The basic flux gauge sensors make a use of non-linear connection between magnetic field H and the magnetic flux density B within a magnetic material. This is the within a magnetic material. So resulting in a change in a material's permeability. What will be the change? The permeability will be changed when non-linear connection between H and B, there is a change in permeability. So this is the winding. This is the excitation winding. This is the pickup winding. This is a basic flux gate configuration. Here we will give the AC excitation here only in a excitation winding. This is the primary primary current. So from this AC excitation, it produces the magnetic field in a pickup winding, and we get the output voltage in a pickup winding only. Okay, so this is what I explained there in the before slide, that is the figure 6 depicts. So next one is a magnetoresistive sensor. Already we had discussed. So magnetoresistive sensor is a two-terminal device whose resistance varies in response to an applied magnetic field. If I'm applied some magnetic field, there is a changes in a resistance. So that is called magnetoresistive sensor. Here is the magnetic material, resistance material, maybe anything. So this is changed when change in resistance across the magnetoresistance material. Okay, if it is increased in resistance, then this material, maybe the displacement or a speed, anything, if consider the speed means the speed is increased. Actually here the magnetoresistance material which is proportional to change in resistance across the magnetoresistance material. So right, so this is the principle of magnetoresistive current sensing. Okay, so the configuration of a magnetic field based current sensor is these magnetic field based current sensors are widely utilized in both closed loop and open loop. So I will explain. So this is the closed loop sensor and this is the open loop sensor. Here is it is a magnetic sensor. We consider this is the primary primary current. So here in closed loop sensor we need a feedback. In closed loop sensor we need a feedback. What is the output? So what will have to correct? For that we need a feedback. So here is the some two set of resistors, maybe we can call it as a CMOS, and here is the amplifier which amplifies the signal and give it to the transistor, and again it give it to the winding. Okay, and also some resistors are connected to measure the voltage, feedback voltage. Okay, this is the closed loop configuration. But in open loop configuration, uh, we do not have any resistor for to measuring the output voltage. Only we have the amplifier. That amplifier directly connected to the output voltage. We don't have any transistor, any switching system, any resistor to get a feedback output. Okay, it only gives the only one output, that's all. Okay, that is the open loop sensor configuration. These are the two configuration which are used in magnetic field based current sensor. Okay, so next one is a fiber optic current sensor. It senses the current using some optical effect. Okay, the Faraday's effect causes the, actually here the Faraday's effect only used for principle of operation. Here the Faraday's effect causes the polarization rotation that is proportional to the magnetic field production along with the line transmission route, that is in the center part. Okay, center part. Here is one is the Faraday effect and another one is a magnetic field projection which will proportional to each other. Okay, by the transmission route, that is the light transmission route. So that is called a fiber optic current sensor. By using the light, it senses the current and gives the output voltage. Okay, thank you for watching. If you have any question or any doubts, please drop the comments below. For more videos, visit our website smit.edu.in and follow our Facebook page SMIT Chennai and follow our Instagram page SMIT Official Chennai. Thank you.